4. So that's the probability that x is 1. 0.278784. So one more to go. You could use the complement rule. If you wanted, we'll just find it directly. It's not too bad to do here. So say we want the probability that x is 2. We'll do just like we did with x is 1. What do the people look like? What are the outcomes that we could see? Well, if 2 of them are left-handed, then that means only one of them is right-handed. So we could have the right-handed person first, and then left and left. Or we could have the left first, and the right second, and a left third. Or we could have left, and right. Oops, that should be a 3. So now the single right-handed person could be the first person or the second person or the third person. And again, since we have the same probabilities, we can find one of these. It'll be the same for the other 2, so we can just multiply it by 3, the number of different ways that we could see this particular outcome. It just happens to be 3 here. It's not always 3. Find one of these, multiply it by 3, and we're done. So for this first one, right-handed, that will be 0.88, then left-handed, 0.12, then left-handed, 0.12. Multiply those together, so you get 0.012672. Okay, and that's one of the probabilities. That will be the same value for these 2. So we just multiply that by 3. So we take 0.012672 times 3, and we should get 0.038016. Okay, and that's the probability that x is 2. 0.038016. Okay. So again, we can kind of take a moment to look at our probabilities and see if they make some sense. So we notice that there's kind of a trend here. The probabilities start off pretty big. This is like 68%, 27%, 4%, less than 1%. So we're decreasing as x gets bigger. So does that make sense? And it does. So what we're measuring, what x represents, is how many left-handed people do we have? Well, only 12% of people are left-handed. So we shouldn't see many left-handed people in our group. We should see more right-handed people. So when x is 0, we determine that that means there are no left-handed people. They're all right-handed. And that's what we expect. We expect to see more right-handed people, so this should be a larger probability. Then as we proceed down, when x is 3, that means what's the chance that all 3 are left-handed? Well, left-handed people are somewhat rare. So having 3 in a group should be somewhat rare, and that's why it's less than 1%. So these seem to kind of follow our expectation. So the last step is let's add them all up. And this can be kind of arduous, but it's worth the time. So we have 0.681472 plus 0.278784 plus 0.038016 plus 0.001728, and we get 1, which is what we want. So this is strong evidence that we've done everything correctly. We didn't rely on the complement rule to find any of these, so these are probably correct. It matches our expectations with the trend that we're seeing, and they all add up to 1. So we're done. Okay. This next example, I'm going to skip it. It's really not that useful. So I introduce a formula to you. Don't worry about it. So this weird U-looking thing is actually the lowercase Greek letter mu. So it's like a lowercase m. And what that stands for is that's a mean. That's an average. And then there's this other formula. Don't worry about it. We've used this formula in example 1. So what this is saying is within your probability distribution, I'm trying to cover up that weird E thing. So this E looking thing is actually the capital Greek letter sigma. So it's like a big S, and what it stands for is sum. So it's telling you to add stuff up. So what it's saying here is we're going to take each little x, multiply it by its probability, and then add them all up, and that will find the average. So there's a little proof to do that. It's not really a proof, it's just an illustration, but I'm going to skip it. It's not that useful. We'll just do some examples with the mean, and we'll see it that way. Okay. Now, this is where the electronic lecture is kind of a pain. This is a really good example. I really like this example, but it's too much work to do by hand. So what's happening here is we're going to look at the probability distribution, and we'll find the expected value. So this is another way of saying mean or average for the Powerball. So this is a lottery game. You pay $2 and you could win millions of dollars. So when I wrote the notes several weeks ago, the grand prize was 90 million. I think now it's 110 million. So the grand prize has gone up. Nobody's won it for a while, so the prize goes up. So if you go to the Powerball website, they give you this chart. So they tell you how much money can you win, and what are the odds, or what's the probability that you win that much money. As well as how you can win that, so what your Powerballs have to look like. So I don't remember the details. Basically, you pick 5 numbers. I think these are from, I'll have to check later. So for the white balls, I think you pick numbers from 1 to 69. They're all different numbers. And then for the Powerball, the red ball, I think that it's 1 through 49. And you pick one value for that. So if you get all 5 white ball values correct and the Powerball, then you win the grand prize. So this is saying the probability that happens is 1 in 292 million and change. So on average, if you played the Powerball over 292 million times, you would win the grand prize once. That's the expectation. Doesn't mean you will, but on average, that's how likely and how often you are to win the Powerball. Not very good. What might be more reasonable is, well, what if you match only the Powerball? So what's kind of hidden here is this means you match the Powerball and no whites. Only the Powerball. So they tell you that that's a 1 in 38.32% chance, and you'd win $4. So if you played the Powerball about 39 times, you would expect to win $4 once. And remember, every time you play, it costs you $2. So it's not looking very good. Now, what's kind of interesting is they're omitting something from this table. It's there, but it's not there. So if I zoom in, just so we can see it, you can see it with your own paper. They tell you the overall odds of winning a prize. Something. Could be 4, could be 7, could be a million, whatever. The odds of winning something is 1 out of about 25. So now we can see that they're not telling us something, and we can figure out what they're not telling us. So there's one prize amount that's missing. What is it? 0. You could win nothing. That is a prize. It's not a very good prize, but it's a prize. So you'd win nothing if nothing matches. So we have to figure out what's the probability that big X, so the amount of money you win, is 0. Well, we know that the complement to this, the probability that we win something, is 1 in 24.87. So the probability that we win nothing is 1 minus, 1 over 24.87, which works out to be 23.87 over 24.87. And if you compute that out, 23.87 divided by 24.87, there's your probability. So the probability that you would win $0 is 96%. So every time you buy a Powerball ticket, you spend $2, the chance that you will win nothing at all is 96%. So then this tells us this 1 over 24 is about 4%. So the chance that you would win something, you don't know what, any of these prizes, most likely $4. So the chance that you win something is only 4%. Not very good. Now, for the rest of the distribution, that's all listed up here. But what we want to know is, what's your average prize? What's the average prize? So if you played the Powerball for a long time, sometimes you'd win 0, sometimes you'd win 4, sometimes you'd win 7, maybe sometimes you'd win the grand prize if you played long enough. So on average, what's your prize? So what we want to do is we want to take each little x, so the little x are the prizes, so all of these are a little x, and all of the odds, these are the probabilities. So we want to take each little x and multiply it by its probability. So for example, let's say we wanted to find, use this row. So in that little example there, we would take the little x of $7 and we'd multiply it by its probability, 1 over 579.76. So we'd get 7 over 579.76, or 0.0121. And these are all in dollars. So we would repeat this process, take 4 times this probability, plus 4 times this probability, plus 7 times this probability, all the way up. Now, some of these are really, really small probabilities. So we do all of those products, we'd add them all up, and that would give us the average price. Now, I've done this. I'm not going to do it here by hand. It's on the Google shared drive. So on the shared drive, there is a spreadsheet. I don't remember the exact name. It's called something like Chapter 6 Powerball Probability Distribution. So you can see that there. So essentially what you'll see, I don't remember the exact value. I want to say when you multiply these all together, the x's and the probabilities, and you add them all up, I think you get something like 70 cents. So what that means is, if you played the Powerball for a long time, on average, every ticket you bought, you would win 70 cents. Not very good when you're paying $2 a ticket. So, kind of glibly, I said, should I invest my retirement savings into Powerball tickets? No. Because for every $2 you put in, you're going to lose $1.30 roughly. So however much money you put in, you're going to end up with less. So it's not a good investment strategy. Do not spend lots of money on the Powerball. It's fun to play sometimes, I guess, but don't expect to win. If you do, great. But now you know 96% of the time you'll win nothing. So not a great game. And these types of probabilities are kind of omnipresent across gambling games and lottery games. There's not a very good chance to win. So just keep that in mind. So we'll do maybe one or two more examples. We have about 12 minutes remaining.